Today's lesson is on ionic bonds, and this is the simplest one to get started on bonding and Lewis dot structures. Basis of it is that electrons give away, atoms with spare electrons will pass them on to atoms that need extra electrons in order to become stable. This yellow electron here gets passed in here to make this one stable, and this one also becomes stable as a byproduct. So it's a win-win situation for both of them. The first thing to look at in ionic bonding is stability, and what is it? In order for an element to become stable, it has to achieve an electron configuration similar to the noble gases. The noble gases are already stable. For other elements, they all aspire to be like those noble elements, those noble gases. In order to do that, they need to have an electron configuration that sort of approximates a noble gas configuration as best they can. The closer they are to a noble gas structure, the more likely they are to be stable. And in order to do this, the best way to understand it is there has to be 8 electrons in the outermost shell. So that's our nucleus. There's our one shell, 2 shells. The key is that the outer one has to have 8 electrons. This one here has to have 8 electrons in it. And you can see here, this guy is pretty happy. He's got 8 electrons in his outer shell. That's the key, 8 electrons. So in order for this to happen, electrons have to be shared or donated by another atom for stability to be achieved. Obviously, if I don't have 8 electrons straight from when I'm born as an atom, me as a chlorine atom, if I don't have 8 electrons now, I'm not ever going to just grow an extra electron. That doesn't happen. It doesn't just pop up randomly. Someone has to give me that electron in order for me to achieve stability. And that's the key here. I need to get that electron from somewhere. And the question then becomes, where do I get that electron from? So Lewis dot diagrams basically used to allow chemists to track the movement of electrons in a chemical reaction. So in order to draw these Lewis dot diagrams, you simply take the chemical symbol of the chemical in question. In this case, we're going to take chlorine. We just write the chemical symbol and draw dots around it. That's all it means. So if I was doing oxygen, I've got O, and then I just draw dots around it. The number of dots that you draw around is equal to the number of electrons in the valence shell. If you look on your periodic table, you see that chlorine is in group 7. That means that it has 7 electrons in its valence shell. If you count these, there are 7. For instance, sodium, potassium, and lithium. Their Lewis dot diagrams all look exactly the same, except for the symbol, because they all only have 1 electron in their outer shell. Bar the symbol, the dot diagram is exactly the same. And that applies for all groups. They all should have the same diagram, except the symbol in the middle changes. Ionic formation. So some elements can achieve stability by taking electrons into its valence shell or by removing them from their valence shell. When this happens, there is an imbalance in the number of electrons compared to protons, and this means the new particle has a net charge. Well, these new particles are called ions. So when an atom gives away an electron, or an atom takes in an electron, there's an imbalance in the number of protons and electrons, you get a charge. So for instance, let's look at sodium here. 1 electron in its outer shell. Now, in order to get 8 in its outermost shell, it needs 7. It needs to collect 7 electrons. Now, alternatively, it could cheat and say, look, you know what? I don't really care about this electron. Why don't I just get rid of it? I'll have a full outer shell because I don't have that shell anymore. So if I lose this electron, I lose this entire shell, which means that now all of a sudden I have a full outer shell. So it kind of cheated. Now, if that was to happen, if you count, there's 11 electrons to start with. Then afterwards, it becomes 10. Its number of protons is 11, and after, it's still 11. So you can see that here it was balanced, whereas here, now there's 1 more proton, which means that the sodium will become the sodium plus ion. And so we've got a positive ion. If you look at the chlorine, on the other hand, it can't pull the same trick as sodium. It can't say, look, I'm going to drop this outer shell, because it's got 7 in its outer shell. So that means that it can just collect 1. And it happens that sodium wants to give away 1. They're both happy. So you can see that it grabbed that electron, this X here, and all of a sudden, it's now got a full outer shell. Now before, it had 8 plus 2 is 10, and it had 17 electrons to start with, and 17 protons. Now it has 18 electrons and 17 protons. So you can see that there's 1 more electron than there was proton. It will become negatively charged. So that's how ionic bonding works. So the chlorine atom and chlorine ion. So let's look at the chlorine atom. It has 17 electrons in total and 7 in its outer shell. So if you count all those dots, you'll definitely see that. In order to achieve stability, it only needs 1 electron more. It only needs to fill this 1 space here. If it does get an electron, there will be 18 electrons, but only 17 protons. And you can see that it's filled with an X here, because that's just an electron from another atom. In Lewis diagrams, you tend to represent electrons from one atom with a certain symbol, in this case circles, and another atom will have electrons represented by something else, say X's. I just like to use that because it helps me to track which electrons are going where. Now this means that the chloride ion will have a net charge of -1. Now the sodium atom and sodium ion, now if we look at the sodium atom, it has 11 electrons in total and 1 electron in its outer shell. It could try to collect 7 electrons, but the key thing is that it could give away its 1 electron and lose that shell. So here it has 3 shells, but here it gave away that electron and has now 2 shells. Since it's easier to lose 1 electron than gain 7, losing electron is more likely. The sodium ion now only has 10 electrons and 11 protons, so the sodium ion has a net charge of +1. So that's why we get positive and negative charges. Now we're going to look at an ionic bond. When an element that gives away electrons comes into contact with one that absorbs electrons, you get 2 ions, one positive and one negative. So if we look at our animation here, we've got one that gives away an electron and one that takes an electron. This one becomes positive, this one becomes negative. So here's our animation. So when the electrons have been transferred, the 2 ions are attracted to one another by electrostatic attraction. So when these 2 form ions, this one's positive, this one's negative, they attract each other, just like opposite poles in a magnet. You've got the north pole and the south pole, and they attract each other. Similarly, these 2 attract one another as well. And that forms an ionic substance. So this attraction is what we call an ionic bond. So when these 2 come together, the bond that they form is called an ionic bond. The substance made up of ionic bonds is an ionic substance. So that concludes today's lesson on ionic bonds. We looked at why certain chemicals give away electrons and why they take them in. And we looked at how to utilize these dot structure and dot diagrams to actually track electrons and to neatly display what's happening in a chemical reaction. So we'll move on to the question segment, and hopefully we can test your knowledge on this new topic that you've just learned. Question 1. In order for a magnesium atom to achieve stability, what must it do? And what is the final charge on the magnesium ion that forms? So in order to do this question, we need the dot structure, okay, or the dot diagram. Or in this case, it's not really a dot diagram as much as it is an electron configuration diagram. So this is not a Lewis dot diagram, this is just an electron configuration. So a magnesium atom has 12 electrons in total. So if we count them out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And as you can see, the first and second shell are both full. The first shell has 2 electrons, the second shell has 8 electrons. Now the outermost shell, which is the third shell, this one, has only 2 electrons. So we need to get to 8 or get rid of those 2. So in order to achieve stability, it could either obtain 6 electrons, or what it could do is remove those 2 and drop this shell completely and only have 2 shells. It's easier to remove 2 than it is to gain 6. It might as well just remove those 2. So after the removal, there are only 10 electrons. So let's just put a cross through these guys. So they're not there anymore. So now there's only 10 electrons and 12 protons. And this means that there are 12 positive charges and 10 negative charges. If you add them together, the magnesium ion will have a net charge of 2+. In order for a fluorine atom to achieve stability, what must it do? And what is the final charge? So again, we draw the electron configuration. So if you look on your periodic table, its atomic number is 9. So it has 9 protons, and it will have equally 9 electrons. The atom, that is. So if you do the diagram, it says in the first shell, there's 2 electrons. There you go, 1, 2. The outermost shell has 7 electrons to make 9 in total. 1, 2, 3, 4, 5, 6, 7. Great. So in order to achieve stability, it could either remove 7 electrons from this shell, or it could gain 1. Now obviously it makes sense to gain 1, then give away 7. It's going to gain 1. Now once it's gained an extra electron, there are now 10 in total. 10 electrons and 9 protons. 10 electrons, 9 protons. Therefore there is 1 more electron than proton, so the net charge of the fluoride ion is -1. Because it's got an extra electron, it has 1 more negative charge than positive charge, so it's a -1 ion. Now for a carbon atom, is it more likely to form a positive or negative ion? This is time for your periodic table to look it up. So what group is it in? It's in group 4. So since the carbon atom has 4 electrons in its valence shell, it can either give away or gain 4 electrons. Now because going up 4 or down 4 is the same number in terms of magnitude, both options are equally likely. The ion that the carbon atom will form will depend on the other atom in the reaction. There's another atom in the reaction. What ion the carbon atom will form will be related to what that other atom is. If the other atom is an atom that wants to give away electrons, like sodium, the carbon atom will form a negative ion. If I put carbon with something that really wants to get rid of electrons, then the carbon will happily accept those electrons and become negatively charged. Whereas if the other case is, if the atom wants to take in electrons, it will give away those electrons and become a positive ion. So you can see for group 4, it's a little bit hard to judge. And that's why group 4 generally doesn't really form many ionic compounds. There are very few ionic compounds made from group 4. So draw the Lewis dot diagram for the reaction between magnesium and oxygen. So magnesium is in group 2 and oxygen is in group 6. So we start with this. Magnesium has 2 electrons in its outer shell, and I represent them with dots. And oxygen has 6, and I represent them with X's. 2, 3, 4, 5, 6. Obviously these two join this one, and you can see there's now 8 in this atom, or ion now, and the magnesium has lost its outer shell. And so it becomes this. It's 2 plus ion and 2 negative ion, so you can see how that works as well. So that's how we draw a reaction in Lewis diagrams. So when ions are formed, what holds the 2 ions together to form a substance? So what actually holds the ions together? Well, when ions are formed, they're oppositely charged because the electron goes from one to the other. Similar to the opposite ends of a magnet, opposite charges attract one another. Now this force of attraction holds the new substance together, so that force of attraction actually holds the new substance together. And this force that holds them together is called electrostatic attraction. So that concludes today's lesson on ionic bonding. We looked at what an ionic bond is, why they occur, and how to represent them with certain diagrams. So hopefully you've learned something about ionic substances. In the future lessons, we'll talk about covalent bonding and the other way atoms can achieve stability with other atoms. So I look forward to seeing you at our next lesson.